Hello everyone, welcome back to another session of Code with a Friend. So today we'll be continuing our journey of learning Rust and we will continue learning about structs in Rust. So I'm using the same book that I've been using for the past few sessions about Rust, but today I'm just using a PDF format instead of the official Rustlang documentation just for a variety. Essentially the contents are same. So let's just dive into this chapter. So a quick recap of where we were. So let me just quickly show the current structure that we have. Um, and this is like a new theme that I'm trying on VS Code. But I was planning maybe I could explore different themes, and somehow I liked this theme a lot, which is, let me just mention the name. I guess what is the current theme? How does it show the current theme, right? I forgot. Yeah, it should be one of them. But anyway, so this theme is quite nice. So we have like a one cargo project because in our last session we tried to make it into a simple file instead of having multiple cargo projects. We will have like one main functions and then different chapters can have their own files. In the main function can be imported using mod then the chapter name, and we can just call the functions in that way. Every time we just be inside tutorial, do a cargo check, we don't actually get any kind of unused variables because everything is usable and all you just need to pass in the command to make it work. Okay, so let's jump into the structure thing. So a structure is a custom data type that lets us name and package together multiple related values that make up a meaningful group. So that's very similar to our C struct or a C++ class or a Java class. Object-oriented language, a struct is like an object's data attribute. So that's exactly what I was saying. In this chapter, we'll compare and construct tuples with structs, demonstrate how to use structs, and discuss how to define methods. Okay, sounds interesting. So defining and instantiating structs. So let's just create just one simple file called, right, and we'll start writing some code into it. So we want to have like a struct user who has a username, an email, a sign-in count, and active. To use a struct after we have defined it, we create an instance of that struct. Okay, so we have like a struct and then we'll create an instance of it. String from, cool. Field init shortened when variables have the same name as fields. If you have variables with the same name as struct fields, you can use field init shorthand. This can make functions that create new instances more concise. And to build user, email string, username, and we can just use that. Okay, makes sense. So this is like a building a function, build user, a build user function that takes an email because the parameter email and username are the same. Okay, this is even more concise. Creating instances from other instances with struct update syntax. Okay, I think we are going too fast here. What are the things that struct wants us to cover? Defining, instantiating an example program using structs and method syntax. I think I would want to start from here, then sort of go back. So we have a length and width area and okay, and refactoring with tuples. Let's start with this. So I think this is like a good thing to start with. So we'll have a public function which just calls area, okay, and So width one will be 50 and let okay, length one is this, width one is 30. Then we have brindle and bang. Area is something area L1 W1 and internal function area. So the length will be a U32 and then the width will be another U32 and that will return a U32 itself. So this is just length multiplied by W. Let's just call it by listing name. So listing name is 57. So let me call this test 57. Let me link the module here. So this part we haven't gotten yet, like how we actually can do this module assignment, but seems like this is working, so I'm using that. And we have 5 dot, oh, let's say 5 underscore area underscore fn. We'll go to chapter 5 test 5 underscore, should be 1, right? I mean, it's a bit odd to put like start with 7. Let's do a cargo check. Test underscore, yeah, that's not the convention. Yeah, I mean, this is an internal convention and following. So I think that should run. So we'll have like 5 area underscore fn and then area will be this. Now we want to refactor, even though this works and figures out the area, we can do better related to each other because together they describe one rectangle. So you can have a tuple. So let's call this function public function test 5 underscore 2. So same thing, but we are modifying with a tuple. Okay. The area and area which is past the rectangle. Function area dimensions. Okay, so we just say it's a U32 which returns another U32 and just do dim.0 multiplied by dim.1. Yeah, this also I forgot, like tuples is actually can be accessed by that, so we can just have maybe 5 underscore area top cargo run. This is actually it's the same thing. So should we just call it area underscore tuple? Five underscore area underscore top. That also works. Refactoring with structs, adding more meaning. We use structs to add meaning by labeling with the data. We can transform the tuple we are using into a data type with a name for the whole as names for the parts. Okay, so now I think we have this. We can just call it struct ret then L u32 W u32. So another public function which test 5 underscore 3 rect1. So we'll have this rect and then just make it L 50 W 30 println bang the area underscore struct rect1 and so, reference of it. Okay, and function area underscore struct rect address of okay, then I think it's fine, which returns u32 okay, 5 underscore area underscore struct. That also works. Here we have defined a structure named it rectangle. Inside this we define the fields as length and width, both of which have type u32. Then in main we create a particular instance of a rectangle that has a length of 50 and a width of 30. Our area function is now defined with one parameter which we have named rectangle, whose type is an immutable borrow of a struct rectangle instance. As mentioned in chapter 4, we want to borrow the struct rather than take ownership of it. That way main retains the ownership and continue using rect1, which is the reason we use the ampersand in the function signature. That is, I think, absolutely clear. Area function accesses the length and width fields of the rectangle instance. Our function signature for area now indicates exactly what we mean. Calculate the area of a rectangle. Another thing is like we are now able to create a struct within this module and access it within that. I think that's fine. So adding useful functionality with derived traits. It would be helpful to be able to print out an instance of the rectangle while we are debugging our program. In order to do that, use a println macro as we have in earlier chapters. So this is interesting. So we can do println bang rect1 is the trait bound rectangle is not satisfied. Yep, that's the same thing. So can do many kinds of formatting, but by default this tells to use a formatting known as display output intended for direct end user consumption. The primitive types we have been so far implement display by default because there is only one way you would want to show one or more other primitive type data. But with structs the way, yeah, so it doesn't know do you want commas or not, how to use that kind of thing. So cannot be formatted with the default format. I try using this instead if we are using a format string. Okay, so okay, let's use this. Oh no. So rect doesn't implement debug. So this is also not working. Rust does include functionality to print out debug information, but we have to explicitly opt in. So if we add this, then it sort of starts working, and we can say 5 area underscore struct. Beautiful. So it actually does like query printing. Adding the annotation to derive debug trait and printing the rectangle instead of using debug formatting. Now we want run the program, we won't get any errors and we'll see the following output. Fantastic. It's not the prettiest output, but it shows the values of all the fields for this instance, which would definitely help during debugging. When we have larger structs, it's useful to have output this. In those cases, we can use colon hash question instead of colon question in the println string. When we use this style in the example, it'll look like colon hash question mark 5 area struct. Amazing. So Rust has provided a number of traits for us to with the derive annotation that can add useful behavior to our custom types. Okay, so I think this is listed in Appendix C. We'll cover how to implement those traits with custom behavior as well as how to create your own traits in Chapter 10. Yeah, we haven't touched what traits is. We have been using it so far. Our area function is very specific. It only computes the area of rectangles. It would be helpful to tie this behavior more closely to our rectangle struct because it won't work with any other type. Yeah. So I guess we're at the end of chapter 5.2, but we can sort of go back to 5.1 a little. So we can define struct, we can create struct, building, yeah, the same way we have created here, tuple structs without named fields and create. So we can also define structs that look similar to tuples. They are called tuple structs, okay, that have the added meaning the struct name provides, but don't have names associated with fields, just the types of the fields, okay. So how they are different from tuples. It's just a naming, right? For example, in this particular case, if I defined a struct like if I define a struct like rectup, which has u32, u32, and I say let this be a rectup of 5032, and I can say dimension is of type rectup. Should it work? It works, right? Which means it's just like a naming thing. Each struct will define its own type. So these tuple structs are basically, it's easier if you have like a very large tuples, you can just use them. What I think it's quite, it depends actually. If you have very large structure, defining like this is not actually very useful, but it can work in a very seamless manner. And in tuples we can't have, I guess, non-primitive types, right? Can we have string in tuples? I doubt. No, I think mismatching is one part, so let's hide that section even in here. It actually allows, so I can have something like this. My house, calculated, calculating the area of dim.2. What about it? Println bang. Warning. Okay. Okay. 5 area tuple calculating the area of my house, but what happens, so this is allocated in a heap, right? And I'm not passing any reference here. Struct val, function borrow val, ampersand value, function eat. Okay. X is value, and reference to value is this. Eat x, then reference to val. Here the function eat takes ownership of x, however x cannot be moved because the borrow to reference to val needs to last till the definition of function borrow. To fix, you can do a few things. Try to avoid moving the variable, release borrow before move. Try to avoid moving the variable, release borrow before move, and implement the copy trait. Copy trait on the type. So here it's borrow, then reference value eat, pass by reference. If it's possible, then we do a borrow, or we can do reference to value is no longer used, so basically swapping. Okay, and implementing copy trait. So you have to just, oh, similarly I believe we did a derive debug trait. We can just do a derive copy trait. Then we can do an X value, reference to value is this. It will be copied here and then borrow. 4 2 references and borrowing. Yeah, so essentially what's happening here is cannot move out rect1 because it is borrowed. So borrow later used here. What if we can we do that? Borrow of rect 1.2 used here and move out of rect. Um, yeah, can we just do this kind of thing? A reference. That is working fine, right? But does it run then? 5 underscore ad underscore struct. Oh no, not this. 5 underscore area underscore tuple. Calculating the area of my house. The area of my house is 1500. Good. Even without that, will it work? Yeah. Interesting. Unit like structs without any fields. Yeah, I think the point that I was making is like we can use um, rect rect up like this. It's a named struct. You can also define structs that don't have any fields. These are called unit-like structs since they behave similar to the unit type. Unit-like structs can be useful in situations such as when you need to implement a trait on some type, but you don't have any data that you want to store on the type itself. We'll be discussing more about this in chapter 10. Okay, ownership of struct data. Yeah. In the user struct definition, we used owned string type rather than the ampersand str string slice type. This is a deliberate choice because we want instances of this struct to own all of its data, and for that data to be valid for as long as the entire struct is valid. To store references to data owned by someone else, but to do this requires the use of lifetimes, a Rust feature that we discussed in chapter 10. Yeah, I don't remember anything about lifetime. Lifetimes ensure that data referenced by a struct is valid for as long as the struct is. Let's say you try to store a reference in a struct without specifying lifetime, such as this. Username, str, email, sign-in count, active pull. Yeah, the compiler will complain that missing lifetime specifier, expected a lifetime specifier. We will discuss how to fix these errors. Okay. Okay, yeah. So I think it seems like the ownership of struct is very similar, which we have tested here. And we also tested how to sort of use struct. Method syntax, yeah, methods are similar to functions. Oh, we can also define methods on top of struct. They're declared with the function keyword and the name. So I think this will be very interesting, right? The area function can be moved inside the struct. And they contain some code that is run when they're called from somewhere else. However, methods are different on functions is that they're defined within the context of a struct or an enum or a trait object, which we cover in chapters 6 and 17 respectively, and the first parameter is always self. That makes complete sense, which becomes like Rust is becoming slowly object oriented. But I think that's like a very popular paradigm. So programmer's mental model might work like that. So in that way, it makes sense to have it, if at all. So can do. Let's do that. So we have impl rect, okay, and the fun area ampersand self, and which will return 32. It can just do self dot L multiplied by self dot W, and we can call it now just the, instead of this we can just call it rect1 dot area. This is beautiful. Cargo check, area struct is never used. Yep, no need of area struct now. Cargo run 5 underscore area underscore struct. Cool. So defining an area method on the rectangle struct, we start an IMPL implementation block, then we move the area function within the IMPL curly braces and change the first, and in this case the only parameter, to be self in the signature and everywhere within the body. In main, where we call the area function and pass rect1 as an argument, we can instead use method syntax to call the area method on our rectangle instance. The method syntax goes after instance we add a dot. Very similar. Okay. In languages like C++, two different operators are used. We use dot if you're calling a method on object directly, and this pointer if you're calling the method on a pointer to the object and need to dereference the pointer first. In other words, an object is a pointer, object to something. It's similar to star object dot something. Makes sense? Rust doesn't have an equivalent of this operator. Instead, Rust has a feature called automatic referencing and dereferencing. Calling methods is one of the few places that Rust has this behavior. When you call a method with object.something, Rust automatically adds ampersand, ampersand mutable, or star, so object matches the signature of the method. In other words, the following are the same. Direct copy clone, point xy f64, distance, self other, ampersand point, x squared, power I, okay. P1 distance ampersand P2. The first one looks much cleaner. This automatic referencing behavior works because methods have. Oh, sweet. Let's try this out. But oh, this function already exists. So we have struct point, a classic structure, f64 and y as f64. We also do a hashtag derive debug copy clone simple point. We have fun distance ampersand self other ampersand point f64. Let's just take an easy example. And we just want to find this person P2. It's unused, so let's just use it. Point distance. Five underscore area underscore point distance. Oh yeah, I have to print something, right? The distance between and is, so what do I do here? Something like this. P1, P2, question mark. Should work? No. Okay. Cargo run 5 underscore area. It's not an area technically. The distance between point is and there's a say 5. Beautiful. What about this? The distance between point and point is 5. So this is because Rust already does this automatic dereferencing. Nice. Methods with more parameters. Let's practice using methods by implementing a second method on rectangle struct. This time we want an instance of rectangle to take another instance of rectangle and return true if the second rectangle can fit completely within self. Otherwise it should return false. Okay, can hold. Yep, so the area is this, can hold is self other. Makes sense. Self.length rather than length. We can just do function square. So it's a specific type of rectangle. Okay. Yep, so I think this is fine. We can start maybe chapter 6 because we have some time till we hit the 1 hour mark. Or we can just implement these functions that we have for more rectangles. I think this is fine. This is quite easy. So let's see how big is this enum chapter. And the enums will sort of complete our getting started section. Then we can go into basic Rust literacy. 140, 134. Let's go going. Where we might want to express in code and see why enums are useful and more appropriate than structs. Say we need to work with IP addresses, currently 2 major standards. Yep. Enumerate all possible values. Any IP address can be a version. Okay, so enum values, we can create instances of this. Like if we have an enum IP address kind, we can say 4 is this and then 6 is that. Variants of enum named namespace under its identifier, and we use a double colon. Both the values are of the same type, IP address kind. How do we print it? So we can enum IP address kind, and we can call this function with either variant. We can call with a root v4 or with a root v6. Using enums has more advantages. Thinking more about our IP address type, at the moment we don't have a way to store the actual IP address data. We only know what kind this is. You just learned about structs, where you might be able to tackle this problem as shown in listing 6.1. So we have enum IP address kind. Okay, address is this, kind is v4, string from, yep, and storing data in IP address kind. We have defined a struct IP address that has two fields, a kind field and of type IP address kind. Okay. Yeah, but what is like it's like an IP address kind is v4. Okay. More concise way is just using an enum rather than part of a struct. This new definition v4 string v6 string. Interesting. We attach data to each variant of the enum directly, so there is no need for an additional struct. That is super awesome. So enum IP address, even we can do something like u8u8, and this can be just a show several defined in our code. Struct IPVRs. We can also do something like this. This is insane. Wanting to store IP addresses and encode which kind are so common that standard library has a definition we can use. Let's look at how the standard library defines IP address. This code illustrates that you can put any kind of data inside an enum variant, strings, numeric, or struct. You can even include another enum. Also standard library types. Okay. So enum, message, quit, move, write, change color. Quit has no data. Okay, so I think the basic part has some no data associated with it. It has some anonymous struct, or you can have like a named struct. You can have a string, 3i32s. Insane. Let me think about it. What we are trying to achieve here. So we can do all of these things with structs. Right. Interesting. We can also write an implementation method body would be defined here. Message write and then call something. Okay, let's actually try to write these things, right? So we have first try with the IP address, all the examples that we had seen, just the code block. So we want to just try out the code block. So enum IP, let's just call it IP. We have v4, we have v6, and let's say first function will have, I can say 4 is just, it's IPv4. That's it. What if I want to print it? Six underscore enum text six underscore. Actually, yeah, we don't possibly need that six underscore in all the functions because it's anyway part of the module chapter 6. So, but anyway, what about this? We have to just provide this derive debug. Should work. v6 is not used. Okay, let me use v6 also. Six underscore what IP enum. Six underscore enum. Okay. Even though it doesn't have any data associated with it, it just prints the enum name. A function should take that value. So if I have like the function just prints the value. And it might have this IP type. IP type is IP println IP type. So what we do here is just to print 4. Can't leak private type. IP declared as private. Huh. Okay. Oh, that is interesting. This is something which also came up interestingly, right? Like if we just do the public function, it was saying the type will be leaked. That is an amazing compile time check. Yeah, love it. So this also works. Can we just take like I mean, what would be the point of taking a reference, right? What about this? Yeah, it's moved. So, yep. I don't need the ownership to be moved. So I think I'm slowly getting the hang of it. Yeah, the movement part. It usually it skips the mind, but so one thing I can see is like you can have subtle bugs, but the compiler will tell you to sort of fix that. So you will fix that pretty quickly. But that ownership thing, by design, in most of the languages, we just don't have that ownership thingy. So we just assume we'll just pass the value. But here, I guess like passing by reference makes more sense. Then you can become flexible. Otherwise, you have moved ownership. So that's interesting. Yeah, this value thing actually quite interesting. Is we can have a struct, which is same. I don't think we need to implement that. But if we can expand this to have a string value, I think the initialization needs to be different. So similarly for this one. Prints properly. So even though we have modified the enum, this function remains the same. That's an amazing thing. We can even make it more complex. Like instead of this, we can say just pass all of these things, and in v4 we have send this. It works amazing. Okay, and even a complex thing like the message part. So we can have a enum which is quite complex like this, unnamed. This is I think a struct tuple. This is a struct, and this is, but it's just like a, it'll have a string data. Message enum whose variants can store different amounts of and types of values. Quit has no data. Okay. Struct quit message. It's a unit struct. Move message. Struct write message. Struct change color message. Variants like the ones listing to similarly define different kinds of struct definitions. Doesn't use the struct keyword. Group together under the message type. Yes, that is exactly right. Yeah. But if we use the different structs, which each have their own type, we would be able to easily define a function that could take any of these kinds of messages as we could with the message enum defined in listing 6.2. There is one more similarity between enums and structs. Just as we're able to define methods and structs using IMPL, we're also able to define methods and enums. Here's a method called call. So we can do impl function call and ampersand self. Okay, the method body will be defined here. So we'll do message write string from hello into m.call, the body of the method. Okay. So what would be, we can define something there, right? So we can have a enum message that has quit, then move x I32 y I32, right, you have string, change color I32 I32 I32. What would we do here? We can just call, I mean, this print function. Oh yeah, this print function, we can just move it inside, right? Let's try to do a print of this one. um let's change it to print, and we want to do a println. If we derive the debug, I'm assuming it will be derived for the structs as well. So we do a println, then this, 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 self dot, yeah, how would we access all of these things? So this is an enum. Yeah, just print the self. Yeah, I think let's see what it does. It's interesting, right? So, and then we should have a public function test6 underscore 2 let. So message can be different. Oh, a message can be a different kind of object or enum. Hello, and we call m dot print. Okay, yeah. Six underscore enum to okay. Six underscore num2, so it goes as right hello, and ideally we should have like different kinds of enum. So we can have message quit, we can have message move, where I define like x is 32, y is 64, 65, anything is fine. And message change color, this is like a struct, so let it be I32. Okay, 255 comma 255 comma 255, and we do print for all of them. uh, where is this? Oh, okay, yeah, I think my struct understanding, yeah, it's should be colon. um X and Y are never used. That That is, I think, fine. That is, I think, fine. 6 underscore num2. Great, great. So we can have different kinds of objects. Okay, and the option enum and its advantages over null types, null values. Yeah, let's just use Rust type system to encode more information than just the data into our program. This section explores a case study of option, which is another enum defined by the standard library. The option type is used in many places because it encodes a very common scenario in which a value could be something or it could be nothing. Expressing this concept in terms of the type system means the compiler can check that you have handled all the cases you should be handling, which can prevent bugs that are extremely common in other programming languages. Programming language design is often thought of in terms of which features you include, but the features you exclude are important too. Rust doesn't have the null feature that many other languages have. Null is a value that means there is no value there. In languages with null, variables can always be in one of two states, null or not null. In Null reference, the $1 billion mistake, Tony Hoare, the inventor of null, has this to say. I call it my $1 billion mistake. At the time, I was designing the first comprehensive type system for references in an object-oriented language. My goal was to ensure that all use of references should be absolutely safe, with checking performed automatically by the compiler, but I couldn't resist the temptation to put in a null reference simply because it was so easy to implement. This has led to innumerable errors, vulnerabilities, and system crashes, which have probably caused $1 billion of pain and damage in the last 40 years. This is, I think, a beautiful paragraph. Like, this actually shows if we, I mean, yeah, what is this I'm doing? I don't need that. Probably the highlight section, but anyway, this actually shows like if there's a tendency to fall towards what is easy to implement and just do that anyway, and sometimes it can stuck. It can create repeated patterns in our programming structure, which creates harder to maintain code. So yeah, it's bad. So the problem with null values is that if you try to actually use a value that's null and not null, you'll get an error of some kind. Because this null and non-null property is pervasive, it's extremely easy to make this kind of error. Sure, the problem isn't with the actual concept, but with a particular implementation. Rust does not have null, it has an enum that can encode the concept of a value being present or absent. The enum is option t, and it is defined by the standard library as follows: enum option t as some t or none. The option t enum is so useful that it's even included in the prelude. You don't need to import it explicitly. In addition, to its variants, you can use some and none directly without prefixing them with option. Option t is still just a regular enum. Some t and none are still variants of type. The t syntax is a feature we haven't talked about yet. It's a generic type parameter. You will cover generics in more detail in chapter 10. Chapter 10 has a lot of concepts. It has like lifetimes and now generics. So generics are, I think, an interesting feature. All you need to know is that this means some variant of the option enum that can hold one piece of data. Here are some examples of using option values. Some number, some string, absent number option I32 is 9. So if we use a none rather than some, we need to tell Rust what type of option T we have. Because the compiler can't infer the type that the sum variant will hold by looking at the none value. Yeah, that is right. Okay, and when we have a sum value, we know that a value is present and the value is held within the sum. Okay, so why is having option T better than, yeah, I think, yeah. In short, because option T and T, where T can be of any type or different types, the compiler won't let us use an option T value as an, ah, Interesting. Interesting. So if you don't, if you have nulls, so it's essentially nuns, your variable which is holding that none will have a very specific type that will be option of that type, and it cannot have the same operation with the typed variable. This is super interesting. Intense. Yeah, this is intense. In effect, this error message means that Rust doesn't understand how to add this to i8 because there are different types. When we have a value of a type like i8 in Rust, the compiler will ensure that we always have a valid value. We can proceed confidently without having to check for null before using that value. Only when we have an option i8 or whatever type of value we are working with do we have to worry about possibly not having a value, and the compiler will make sure we handle the case before using the value. In other words, you have to convert an option t to a t before you can perform, which means you have to initialize, you have to assign some values. It cannot be non-null. Not having to worry about missing an assumption of having a not null value helps you to be more confident in your code. Absolutely. In order to have a value that can possibly be null, you must explicitly opt in by making the type of that value to option t. Then when you use that value, you are required to explicitly handle that case. Makes sense? So how do you get the value t out of some variant when you have a value of option type and you can use that value? Option t enum has a large number of methods that can be used in a variety of situations. You can check them out in the documentation. Becoming familiar with the methods, yeah, in general, in order to use an option t value, we want to have a code that will handle each variant. We want some code that will run only when we have the sum t value, and this code is allowed to use. Yeah, cool. I think we're already over than 1 hour today, so I'll end the session today. Let's meet in the next session and understand like the match control flow operator. See you in the next session. Bye bye.